All right, the area of process control, some of the ideas, the possibilities, again, in an integrated circuit, induction heat treat, a lot of heat involved there, die casting, certainly, welding, laser processing, moisture measurement, and melt temperatures. This was a sewing job. Got a call from Delphi. We've got a lot of seats, and the stitching is coming apart right at the corners. After somebody sits on our seats for 50 times, the stitch breaks, and it's a warranty repair. And they hired the University of Windsor, and I got called in, and we did a wonderful study. I brought in my cameras, I laid it on the side so I could get down close to where the needle was going in and out of different materials. And we ran all kinds of data here, materials, multi-layer materials with foam and plastic, all kinds of needles at different speeds and stitch speeds and things like that. And we introduced things like air vortex cooling, just to understand why that stitch was breaking only at the corners. Along the long runs, it was fine, no stitch break. This is a close-up. I tried to paint the needle with black, but it only lasted a couple of stitches. It would wear the paint right off. So how do I get a nice, shiny, hard steel, perfect needle to emit so I can make some measurements? The thread was no problem, but that needle was a stinker. So my camera was sideways, so the needle is going this way in this data here. You can see the nice tip of the needle. Now I had a nice blow-up of what that image looked like. Here's the thread that's going through the eye of the needle right there. And then the thread continues on behind the needle. So as it's stitching, in this case it was, we call it a slow speed. It might have been 200 inches a minute or something like that. We were grabbing data. We could see the thread, 40 degrees Celsius. It would go through the eye, and look what's going on in the eye. All thread has a sizing on it. Trying to put that thread through a needle, it's like a cow catcher. It's going to catch some of that sizing. So around the eye of the needle, lucky for Dan, I had a good emitter. So I could zoom in on that, seeing what the temperature of that needle was getting up to very, very nicely. So I didn't have to rely on a coated needle. It would coat itself in the right area, right at the eye. So we studied this. We got a couple of wonderful papers out on it, printed worldwide in a couple of journals. We solved the problem, and Delphi was extremely happy. University of Windsor got paid for the study, and they were very happy. And I was happy to work with the students there and some of the researchers. This was the only time I ever was able to cross the border with equipment filled in my back seat, and customs never gave me a problem. Where are you going, sir? University of Windsor, go right ahead. Working with your students, they love that. So anytime an industrials researcher can help the Windsor students, our Canadian customs are all aboard for that. I never had a problem. So it's pretty fun to have that kind of support.
What was the solution?
Very good. I forgot to get to that. That air vortex cooler I showed you on the machine, that was in the industrial sewing machine. They had it hooked to the foot pedal, so when they lifted up the pedal to turn the corner, the air vortex cut off. The needle dumped all of its heat into the thread at that point. Simple. Once we seen what was going on, we understand the heat that was going into the thread, you just leave that cooler on, no more problem. Simple fix, okay? It's usually that's the case. It's Occam's razor, it's simple things. There's nothing complicated out there, folks. It's simple stuff. It really is. But until you see it and understand it, it's tough, because you're shooting blind otherwise. So that was a fix. Any other questions on that? This is a transmission part. It goes through a very intricate stamping to get that deep draw. So it's from a flat metal, it's got to be drawn out very nicely. Well, you can see the oil in here to lubricate the drawing process. GM was switching over to another oil supplier, and they had a hiccup. They did this on another set of dies, and the oil wasn't designed right to take the temperature that the stretched metal was delivering. They oopsed about 12 sets of dies and lost a lot of money. So they weren't going to do that again. I got the call. What's that surface reaching during the deep draw? What's that oil have to meet spec-wise? So I set up, I'm looking at all the different die draws that they're doing, getting a temperature during the draw process. A nicely thick coated oil shiny surface becomes a fairly good emitter, and we can make a measurement on that. You can see now the draw die was thicker at the top here and then flowing down, thinning out. But we're able to get a temperature reading off of that thicker oil coating. Organic material is a good emitter if it's thick enough. And things like grease, oil will work fine, but you got to make sure there's enough on there. So in this case, we were able to get the temperatures off, tie that to our manufacturer spec that we needed, and the manufacturer then was their responsibility to make sure that the oils didn't thin out at these kind of temperatures to ruin those dyes. And it was successful. They had no other way. You can't put a thermocouple in there. You're trying to reach it. They don't react quick enough. How do you do that? Well, you do it at 60 frames a second with a thermal imager, making sure the oil was thick enough. So in some cases we had to get a little more oil on it, but it worked out fine. This one application, this is my highest cost savings ever. We lost $43 million in 1 week, shut the plant down because of this process. This was a hot melt glue process. This robot was shooting out this glue at such a speed, this thing was flying. This robot was a blur, but at every time it reached my end of the table, it had to stop and go the other way. Guess where I was sitting with my thermal camera? So every time it stopped, I'm taking data as fast as I can to capture what's going on in this thermal melt process, melt glue process, and why are these panels coming off when they're not supposed to. Oops. This was at a supplier. They thought they were doing a good job. This glue was supposed to be over 400 Fahrenheit in their cookers. So it goes through the whole process, through these transfer lines. We look at the boiling oil and we lift off the cover and 400 degrees right on. We study it as it's going through the robot. We're seeing 400. I go on front here and I'm not reading 400. Coming out was 284. And by the time it hit the panel, it was down to 180 degrees Fahrenheit. I called the vendor, he says it won't stick if it's below 240. I think I know the problem. We're too cold. Oops. So what it turned out, there was a buildup in this glue in the nozzle. There was a layer. And if you can just imagine a laminar flow, they had a laminar layer of glue lining those lines. They didn't take the time or the effort to clean all those lines out all the way to where the heaters were on the outside. So as you build up a layer in there, it wasn't heating the inner flow where that molten plastic. It was coming through there maybe 284, not 400. So the heaters were trying to do the job. The original melt temperature was 400. By the time it got to this nozzle, it lost, 116 degrees just in transfer and a build-up boundary layer of old glue. So we got that straightened out. We were up and running and making good parts before I left the plant. I was in my lab typing these up and people were grabbing at it, trying to get it off the printer, running down the hallway to get the plant back up and running. So it was a wonderful experience. You have things like that occur when you're shooting infrared. Pretty exciting, and things like that, when you can solve a $43 million problem, you feel pretty darn good, you know? Yes, sir.
In a predictive way, could you have been monitoring the buildup to know when to replace?
That's pretty tough. You could do this, right, if you watched what was coming out the nozzle. You could go once a day, beginning of every shift. You could even do a little NDT, pull off a panel, let it cool down, and see how it sticks. Well, that would be more destructive. But scrap one out twice a shift. If it's not sticking, get out the camera and look. But you're gonna have to get at the end of that table, and you're gonna have to shoot as fast as you can because that thing is flying. All right. I was lucky to get this kind of data. It was just luck. Yes, sir.
I'd be curious, what percentage of the time do you find that the movie camera, where you're taking, moving pictures of it, is more elucidative or better for troubleshooting than single shot pictures?
I use moving pictures probably 98% of the time now. It's actually, I've always done it with moving pictures because you want the exact, or the couple of those thermograms that capture everything you need to capture. And with hundreds of images, as you stream through, you can pull out the peak, the absolute peak. You can see things happening before you get to that peak. You can watch cool downs. It's just digital storage, and digital storage today, we can get terabit storage and document stuff and store it away for $100 a terabyte, It's simple now. I've got the world's biggest, this was all on videotape years ago. I've got hundreds and hundreds of videotapes. It's just stored away. I don't know what else to do with them. All full, everyone's taped to the nth, with data like this, and we used to analyze them all the time, or hire people. And some of our studies were so huge, I had to have extra people to come and run analysis for me because I couldn't stay all those hours to analyze all the data tapes. So the data's there, and in motion pictures is really, I think, the way to go. Thinking like a bus duct, if you're running predictive, then you can find a bus duct and take a picture, okay? If, like an injection molding machine, you might do a video on that, or just wait, watch it, and freeze an image. If everything on your frozen image looks good, store it. If not, erase it and wait for another freeze frame. A lot of stuff today, one of our advantages with machine vision is, don't get me wrong, I'm all for the labor and for making manufacturing back in the US, but we got to do it smarter. If we're going to do it smarter, we've got to use tools like machine vision and infrared so that we can compete worldwide, get some of the cost out of those parts. So machine vision and infrared, man, it's like it's the answer to some of our problems in competing with world economy and our manufacturing costs. Cutting the cost out using machine vision and infrared is the way to go, and it's all there. Just doing it smart, and the data's there. It really is, and the costs are down. So it's really the time to really get involved in this. So I have a thermal image up there, and I'm going to ask a couple questions and see who gets to eat their cupcake and who doesn't. So if we look at the temperature range, red's around 98, 99, and it looks like hot water flowing out of a faucet. Okay? Everybody agree with that? All right, good. So for the non-thermographers in the room, thanks, Bruce, we've got a faucet carrying that 100-degree water, and boy, it doesn't look red, does it? Why? What about that material that faucet's made out of? High reflectivity. So, and it's curved. Couple of,
Is that plate part?
yeah, that's chrome plated. So very, very high reflectivity, curved surface. So instead of giving off the heat that it is, it's at 100 degrees, same as the water. That's been running for a while. It's just rather reflect background radiation into the camera. All right, so the water's flowing into the sink, and we see it puddling up here. The sink, I'll give you a hint, is stainless steel. And this is a soap dispenser, that's chrome. and the faucet down here is chrome. So if this is the hot water, what do we think this might be for the non-thermographers?
Some sort of soap blower or a filter?
No, not a film. That's the next question I have. That's reflectivity of the hot water off of the stainless sink. So here's our source. It's reflecting off of this stainless sink into the camera. So one way to measure reflectivity of that sink then is to catch the temperature here, catch the temperature there, divide one by the other. We know reflectivity of stainless steel now. We can use that. 1 minus reflectivity is emissivity. So if we had to measure it, but I have a few rules of thumb, and we're going to get to that later today when we talk about machine vision. And then the third thing, we've got a couple of black dots here that is kind of your idea. That's neither reflectivity nor hot water. It's just cold water drops that have splashed and cooled down, and water is a wonderful emitter. It's like human skin, it's 98% efficient. So human skin's good, water's good. If you walk out on a sunny day or in front of a campfire, you feel that heat right away. So you're a good absorber. If you're a good absorber, guess what? You're a good emitter. So wear your hat in the winter, because your head's going to be emitting like crazy, because your skin's a great emitter. All right, any questions on that? You've got to understand emissivity and reflectivity to utilize infrared technology. You've got to understand it. Yes, sir?
I keep sorry to interrupt, but this is the sort of, for at least the plastics industry, we're just getting introduced to it. And what I have found in my career with plastics is people see these cameras, they immediately want to go after the mold and things like hot tips.
Right.
And please listen and remember this picture. They get turned off because they go after it, then they find out it's not giving them the right information. They don't know how to look at it. They're looking at these reflections that you're seeing. So therefore they say it's not good technology.
That's right.
I've been fighting this for more than a decade, not making my progress. Please don't do unpainted metal for
Right.
folks.
Right. The only time you can do that is in die casting. There's a patina built up on a die cast mold, the injection mold, from all the lubricant. It's charring and a patina, and it's a good emitter. 0.92, 89 to 92. When I shoot die casting, I do about a 50 spot measurement of emissivity. I take an average emissivity, and then I avoid any flat, shiny areas. I don't even want to go there on a die casting. But injection molding, look at the part every time. You're not going to see it, unless there's geometric reasons. Bolt holes, seams, threaded holes, corners, places where things meet up with others, that seam is a good emitter. It's just what I call geometric emissivity enhancement. And look for the geometry. If there isn't any good geometry, you're out of luck. You got to coat it, or look at the part popping out, or in some cases you're just out of luck. You know, you can't, no matter what you do, you're out of luck. But there's always tricks. You know, there's subtractive techniques. If you have a low emissivity, high reflectivity, if it's not too bad, sometimes subtraction will work. There's some real subtle signals that you can pull out with subtractive techniques. But it's a little more luck there than anything else, okay? Most times we've got to coat it if it is a high reflective surface. We can coat it with powder, tape, stick-ons, poster paint, oil. There's tricks up a sleeve that you can utilize to make it a good emitter, and then you can go to town.